All right, hello, my friends, my compatriots. Today we're solving LeetCode 17, letter combinations of a phone number. Given a string containing digits 2 through 9 inclusive, return all possible letter combinations that the number could represent. Return the answer in any order. A mapping of digits to letters, just like the telephone buttons, is given below. Note that 1 does not map to any letters. So as you can see in this first example here, these are all of the possible mappings of letters if you typed in the digits 2, 3. Because 2 maps to ABC and 3 maps to DEF. So each one of these outputs should be of length 2, corresponding to the 2 and the 3. And these are all the possible combinations of said letters. All right. So I copied over the phone book mapping, and we have the problem here. And this is a backtracking problem, so you should remember that all backtracking problems can be modeled with a decision tree. And since we're returning strings, we can think of the first decision tree as just an empty string. Now, what option do we have from the empty string? Well, first, since the first number is 2, we want to loop through all of the letters that correspond to 2. So the first option would be to choose A, right? Now, from A, what options do we have to choose? We can't choose another letter that is mapped to 2 because the digits are 2, 3. So we have to find a letter that maps to 3. So in this case, we'd go A and then E, right? Because we have the first number maps to A and the second number maps to D. We did AD. We see that AD is of the length of digits. So that means we have one letter that corresponds to each number. So that means we backtrack back up. We're back at the A. And now we can choose A, E. So AE. Perfect. We backtrack back up because of the length of digits. And now we can choose A and F. So hopefully you can see the pattern here. First, we choose one letter from the first map. And then for the second number, we look at that map and we iterate over them and add it in. So this is the entire tree if we chose A for to be our first letter. Now what would happen if we chose B? Because B is now the second letter that maps to 2. So we choose B, and what happens here? We can choose B and D. We can choose B and E. Or lastly, we could choose B and F. So hopefully you recognize the pattern here. Every letter that maps into 2 will map to every letter that maps to 3. And lastly, it's the same exact thing here. We choose the C. So if we choose C first, now C could be mapped here, and the 3 would represent the D. We reverse back up and we choose the next option, so C and E. And lastly, C and F. And as you can see, AD, AE, AF, BD, BE, BF, CD, CE, and CF is equal to the output here. So this is all of the combinations of letters that we can make with the digits 2 and 3. All right. So you might be wondering, all right, I understand the decision tree. I understand how you got here, but how do we code it up? And that's why I'm here. But first, before we do that, let's go into what's the time complexity would look like. It would be big O of 3 or 4 to the n. And you might say, what does this mean, 3 or 4? 3 or 4 represents the length of the mapping. So some numbers are mapped to 4 letters, like 9, and others are mapped to 3. So depending on what you get, it could be 3 or 4. So that would denote the number of branchings or the branching factor. In this case, both of our numbers only had 3 letters mapped to them. So that's why there's 3 options here. So 1, 2, 3 for every single option. So there's 3 up here, and every child has 3, right? And the n represents the depth of the tree. And n is just the length of the digits. In this case, it is 2. So as you can see, 0, 1, and 2. So the exponent represents the depth of the tree, and the base represents the branching factor. All right. So now that you understand that, let's get into how we'd code something like this up. First, what I like to do is complete our res array, because res is just going to hold all of the combinations. Next, what we will have to do, which isn't too fun, is we have to make a mapping that looks like this, that has every single letter that maps to every single number. All right, and I'm going to quickly do that for you guys, and I'm probably going to skip ahead so you guys don't have to sit there and watch me do this. All right, so here we have our mapping, and our mapping is essentially just this number pad here, but in code. So the computer knows that 2 maps to ABC, 3 maps to DEF, and etc. And you can quickly look at this and copy it down, but I think I'll speed up that in post-production so you guys don't have to sit through that. All right, so now what we need to do is create our DFS function. So define function DFS, and we're gonna need a couple things. First is S, this just stands for the string. And next we need a start to know what number we're supposed to be iterating through. Because when we first start, we're iterating over the 2 to pick the A, B, and C, but the next letter has to come from whatever the next digit is, in this case 3, to get the DEF. All right, so since it's DFS, that means we need a base case because DFS is a recursive function. So if the length of S is equal to the length of digits, then we want to res.append S and return, right? So just like when we were here, as you can see, the length of AD is the length 2. The length of our digits, 223, is 2. So that means we have 1 letter for every number in digits. So that means we're done because 1 letter maps to each number, right? So that means that's when we want to append and then continue. Next, we need a for loop that's going to be able to actually pick these and append them onto our string or add them. So for letter in map at digits at start. All right, and to quickly explain what this does, if starts off at 0, we're going to say for L in map at digits. So we check digits and we say, what's digits at index 0? In this case, it would be 2, and the first letter would be A. So we're going to add A to our string, right? So that will make sure that's there. So now we have to call DFS, and we can go string plus L, because if we start off with an empty string and we add the letter, we'd have just the A, right? But now we have to send the DFS call and make sure the next letter it adds comes from the next digit. So in this case, at 2, the next digit is 3, and we need to make sure to try to get the D, right? So we say start plus 1. If start was 0, the 0 index, which would represent the 2. If we say start plus 1, it would represent the 3, and we get the first letter, so D. So that would be A plus D would be AD. And if you go back here, this is the first combination that we have that's valid, right? We'd hit this append line because the length of the string is equal to the length of digits. We'd return back up, right? And then we'd add the second letter. So we'd go A and then E. And as you can see, AE is the next one. So hopefully that's making sense on how this DFS works. In most depth first search or backtracking functions, we always have append and we pop. But in this case, we don't have to do that because we're using a string. We can just simply add it onto the string. And once the DFS call ends, it's like we never added it. So there's no cleanup work. Now, what we have to do is call our function. So we say DFS with an empty string and the start of 0. And we have to return res. So let's try this out and hopefully it works. All right, and it runs and it's pretty efficient. It reaches 100% of runtime complexity. So I hope you enjoyed the video. Drop a like if you found it helpful. Peace.